share the screen from Zoom. Oh, okay. Yeah, so go into Zoom. Share screen. Here. That one? Yep. And then what we do is we can go into presentation mode. All right. Is it going to work? Yes, it is. All right, brilliant. Okay, so we've had a slight change of the program, but not to worry. So we've got Gowrie here, and Gowrie is a lead research fellow at the. I brought this up because it was research fellow at the Distributed Systems, Blockchain, and IoT Trusted Networks Lab here at QUT. Yeah, and so please take it away.
Thanks for the introduction, Peter. All right, good morning, everyone. Yeah, so it's a tough one to follow after Tina's talk. I'll do my best. So my talk is going to be in the context of applying blockchain to multi-stakeholder applications. So where the data sharing and trust also plays a critical role. So I'll be going through some of the work that we are doing and did in this space, and also, going to talk about the open challenges that we still need to resolve to have trusted applications for trusted multi-stakeholder applications. So before I get into the solutions, I'll briefly talk about what I mean by multi-stakeholder applications. If you look at supply chain applications in the real world, for example, on this slide, I have a supply chain application for tracking medicines. So in this particular application, you can see that there are different stakeholders, and between these stakeholders, a lot of information gets exchanged, and this information includes the expiry date of the medication, where the medication was created, and what process was followed, and so on. So you can see that this information is critical for the operations in this application setting, because based on these decisions, these stakeholders in the supply chain, plan their operations and serve the end consumers or customers. So therefore, the point that I want to emphasize here with this slide is there are many stakeholders, and a lot of information gets exchanged between these stakeholders, and this information is critical for their business. And similarly, here is another supply chain application, but this time in the context of agriculture or agri-food. Again, here you see number of stakeholders, and again, they are sharing information to properly track the food product throughout the supply chain, because they want to make sure that the food products are not tampered with or mishandled during the supply chain. And also they want to ensure that there's no contamination. Therefore, they want to closely monitor the food product throughout the supply chain. Again, the same thing happening here. There are many stakeholders, and we need to ensure that the products are handled appropriately throughout the supply chain. Therefore, we need to have information sharing happening between different stakeholders. So again, with that, the point that I want to emphasize upfront is that many of these real-world applications increasingly operate in multi-stakeholder environments where there is a need for information sharing, and this information is very critical for the businesses. But then if you look at the systems or the digital systems that are driving these real-world applications, especially in multi-stakeholder environment, at one end, you have the data or service providers. So these are entities who are providing data for the other stakeholders in the ecosystem. At the other end of the spectrum, you have the data and service consumers. So these are, again, stakeholders who are consuming data and services as part of this multi-stakeholder ecosystem. And what is connecting these data and service providers with the data and service consumers is the centralized systems. And that's what we've been used to for the past 2 decades. We mostly relied on an application that was running on a server, and all these different entities were actually relying on the centralized system to exchange information or exchange services. And typically, these centralized systems are controlled and managed by one organization. And when we rely on this one organization, we are running into this single point of failure problem, where that one organization that is managing the infrastructure, if that organization turns out to be malicious or corrupt, or in some cases, the infrastructure itself is attacked by some cyber attackers, then we have the single point of failure. Okay, so if that centralized system fails, pretty much every application that relies on that centralized system is going to fail. Okay, so we are not going to have a reliable infrastructure for exchanging data or services among these different stakeholders. And that's the problem with centralized system. So this is where, in the past 5 to 6 years, many people started building blockchain-based systems for these multi-stakeholder applications, where they got rid of these, mediators, and the mediators was centralized systems before, that centralized server. Now they introduced blockchain technology. And now these different stakeholders are actually relying on this blockchain technology for information exchange. And the reason why they opted for this type of an architecture is because of the transparency that the blockchain offers. So between these different application stakeholders, you can set up a ledger that can be public, meaning that these different stakeholders can look at the operations that are being handled through this ledger. And it also provides this immutability property, which means that once you write the data to this ledger, it cannot be modified. Okay, so it's a write once ledger. So this is an important property that blockchain offers. Yes. Oh, please, sorry. Oh, there's a technical issue for the Zoom attendance.
Because if you do it in the screen presentation, it wouldn't move.
Okay, now I can do it. Is there a way to check?
Yeah.
Are we sharing the present that one up on the screen itself? Okay, sorry. I know what to do. Just a few seconds, everyone. Okay. So we need to do and then we can share. Sorry about that.
Is it fine now? All right. All right. Sorry for the interruption. So yeah, what I was talking about. Now I'm unable to switch slides.
Oh, okay.
Maybe I do it like this. All right. So what I was talking about is, we moved from the centralized systems to these blockchain-based systems, where we relied on these blockchain ledger to sort of enable interactions between the data providers and data consumers. And the reason why this technology was opted in the first place was the transparency property that blockchain offers. So it provides an opportunity for all the stakeholders to look at the activities that are happening as part of their business. And also immutability, meaning that the transactions once written to the blockchain, it can't be modified. And this is a very important property of blockchain that benefits these type of applications. And then it also provides trust guarantees because the operations are not controlled and managed by a single entity. By default, it follows a decentralized architecture. That means that all the operations of the blockchain technology is actually distributed. Okay, there are multiple parties or computers involved in the operation of blockchain itself. Therefore, it provides a high level of trust guarantees for the applications. And because of these features, we actually moved to blockchain-based systems. But then we also have this problem with the blockchain-based systems, So if you look at this slide, at one end, you have the blockchain technology or the ledger that can allow you to, store and manage information in a reliable fashion. But the other end, we have all this, data sources that connects to the blockchain. Okay, so the blockchain can hold your data, but blockchain does not have the intelligence to distinguish between credible data and fake data. Okay, it can do certain things for you, but it lacks intelligence. Of course, we have smart contract, but it's not exactly smart enough to distinguish between information that is fake and the information that is actually genuine. So we still have that problem. So at the other end, we have these different application data sources and that are being pushed to the blockchain as part of these multi-stakeholder applications. But then we have this problem of garbage in and garbage out, meaning that the blockchain technology can store data, but it can also store garbage data. Okay, so when you request data from the blockchain, it can give you the data, but it could be a garbage information, meaning that it could be a useless or information that you cannot rely on. Okay, so this problem is highlighted as garbage in and garbage out problem in the blockchain landscape. So we need to have solutions that can help us mitigate this garbage in and garbage out problem, so that the data that gets pushed to the blockchain itself is reliable, or at least some way for us to check which parties pushed the data to the blockchain, and we can actually make them accountable if there are any issues in the future. Okay, but then we need some solutions. Okay, blockchain can store data, but it cannot distinguish between good and bad data. So that's the problem that I want to emphasize here. Therefore, we need solutions that guarantees end-to-end trust. So that means that from the data source all the way up to the blockchain, we need to have solutions to guarantee trust. And this is where we are carrying out some of the research work here in our Trusted Networks Lab at QUT. So our focus is on building trusted data sharing and trusted computation solutions that sits between these data providers and the blockchain technology. And with these solutions, what we can do is we can provide some additional level of trust guarantees. At least you can verify that the data that got into the blockchain ledger is credible and something that you can rely on. Okay, and these are our important focus areas here at Trusted Networks Lab, among other topics. We also do work in the space of privacy and other issues in the context of network systems. But yeah, these are like notable areas that I want to emphasize. In particular, the solutions for trusted data sharing or Trinity, which is a platform that I have developed recently. This is to enable trusted data sharing involving legacy systems. And another interesting work that we are currently doing here at QUT is performing consensus by having human in the loop. And this goes back to the point that the smart contracts are not smart enough to handle some information. Therefore, can we have human in the loop to provide some additional trust guarantees for multi-stakeholder applications? And the other thing in the space of trusted computation is we are building verifiable computation, which I will talk about briefly. But again, here, can we also have some methods to verify the correctness of computations? So these are the technologies that we are currently working on here at QUT. And this talk is going to briefly talk about these three solutions that we have created. So in the interest of time, I'm not going to go into the nitty-gritty technical details of these solutions. I'll sort of provide a high-level overview, but then if you're interested, I'm providing some pointers. And also I'll be available to discuss after the talk. The first one that I'm going to talk about is Trinity, which is a trusted data sharing platform. This is based on the work that we presented at a conference about 2 years back. So this work is in the context of publish-subscribe communication. For those who are not familiar with this communication protocol, this protocol is widely used in real world applications for connecting different data producers with data consumers. Okay, if you take any application in the real world, you have the concept of data producers and you have the concept of data consumers. You need some methods or some technologies to connect these two people. And this publish subscribe communication model uses something called a broker. This broker acts as a mediator, and this broker connects the data producer with the data consumer. Okay, so this is widely used. Many supply chain applications already rely on this publish subscribe communication model in the real world. But the problem with this model is that this is also relying on this centralized broker. So the centralized broker is still going to be susceptible to the central point of failure. So if this broker is compromised, then all the data that gets shared between data producers and consumers are going to be compromised as well. So I'll give you an example. Let's say that the data producers is sharing information saying that the temperature of the container that's carrying a food product is 12 degrees Celsius, okay? But then if the broker is compromised or malicious, that broker can actually tamper with the information. It can delete 12 degrees Celsius and instead replace 8 degrees Celsius for financial gains or for some other reasons. And then the consumers or the data, the ones that are relying on the data, they may be receiving information that says temperature is 8 degrees Celsius, okay? So if you rely on this broker that is centralized, we have no visibility into what is happening, okay? That broker can arbitrarily tamper with that information. Therefore, we have no way of verifying the correctness. This is where we introduce Trinity, which is a platform that we have developed. So here what we are saying is connect the broker with the blockchain technology, whereby when the data publishers produce data, they will send the data to the broker. The broker would then relay that data to the blockchain technology. Therefore, the copy of the data is available in the blockchain ledger, okay? When some data consumers receive that data, they can be guaranteed that the copy of the data is available in the blockchain ledger. If they are still suspicious, they can go and verify whether that data is available on the blockchain, okay? This way, they can ensure that the data is not tampered with. That's one thing. From the publisher's point of view, they can also go and verify whether the data is correctly available on the ledger, because ledger is public. Before, with the broker alone, the broker was not public, it was private, okay? That broker was not providing any transparency to the other parties in the ecosystem. Now, by connecting the broker to the blockchain, you are providing some level of transparency, and this transparency is allowing the data producers and data consumers to verify the integrity of the data. So again, in the interest of time, I'm not going to go into the nitty-gritty details of this work. The detailed protocol and the implementation of this broker, including the open source software, is fully described in this paper that we published. And I would encourage you to read this paper, and also feel free to discuss with me if you have any questions, or if you want to better understand the operations of this and how we are providing trust guarantees in the Trinity context. And now moving on to the next framework that we are currently developing here at QUT. This is an email-based and human-centered consensus for multi-stakeholder applications. So again, I was talking about smart contracts and how you can use smart contracts to perform some operations as part of your multi-stakeholder applications. Let's consider supply chain as an example. There you can write down some of your supply chain logics into the smart contract. So when the transactions gets processed by your blockchain, your smart contract can actually apply those rules and see whether the transaction is fulfilling the requirements that are captured by these rules. Okay, so these rules are basically, if the product has reached the supply chain endpoint at the right condition, transfer the payment to user A, for example, is a simple rule. Okay, so these kind of things can be automated with smart contract. But what smart contract cannot do is whether this information that it receives is credible or not. Okay, it cannot distinguish that. Okay, it will operate based on the information that it receives. So what we want to enable with this work are the human in the consensus, so human in the loop work is have some human involvement in these decision-making process. Thereby, we are adding some additional credibility to the information that goes through these blockchain-based systems. Before I explain the protocol, I'll briefly introduce the blockchain consensus. So again, I'm not talking about proof of work, this or that, but I just wanted to provide an introduction at a high level. And then in the blockchain context, the consensus algorithms are there to help nodes agree on the state of the system. Okay, so that's their role. Okay, in a blockchain system, when you're performing any transactions or operations, you're relying on a system that is coordinating or collaborating with multiple nodes, and there these nodes are actually jointly running an algorithm to ensure that there is consistency. Okay, so everyone has the consistent view of the system that they are part of. Okay, so that's what it ensures. And here in this context, Byzantine fault tolerant consensus is one type of consensus. Okay, there are other types of consensus algorithms, including proof of work, where it performs some kind of leader election to perform consensus. But again, I'm not going into the details there. But I want to talk about Byzantine fault tolerance briefly because that's relevant for what I'm going to talk about next. So this Byzantine fault tolerant consensus rely on a group of nodes, okay, like any other consensus algorithms. But the key thing here is if you have 5 nodes like the one you see in the slide, when you use Byzantine fault tolerant consensus algorithm, you want more than 2/3 of the nodes to approve something or agree on something. For example, if you say temperature is 12 degrees to these consensus nodes, then they will all have to look at that information and sort of come to an agreement that they have all seen that information. We are approving this as a credible information. Then the consensus process is concluded. And once the consensus process is concluded, the information gets stored in the ledger. Okay, so that's the process that blockchain follows typically. So therefore, in any blockchain systems, consensus plays a critical role. Okay, before the data gets written to the ledger, there is this consensus process. And this is what ensures that we have some consistency and we have some transparency in the operations that are happening at that layer. So the problem with this Byzantine fault tolerant consensus is this process lacks intelligence, meaning that if you say temperature is 12 degrees, everyone will be looking at that information and everyone will come to consensus. They won't go and check whether the temperature is 12 degrees or not. What they are agreeing on is temperature is 12 degrees. That's the information that they are agreeing on. And they would all, compare the hash of that information and ensures that it is consistent. And then they go ahead and store that information into the ledger. Okay, so this is sort of a rule-based approval where you have, if you have approval from more than 2/3 of the nodes, then you go ahead and store the transaction in the ledger and move forward. So with that introduction of consensus process, what we want to build is we want to remove this rule-based consensus that are prevalent in these systems and substitute those rule-based systems with email-based consensus, because many of the business managers, they use emails during their businesses, every day pretty much. So what we want to do is, can we connect some of these consensus logic or consensus operations to the emails so that, whenever some decision needs to be made as part of a business process, we would trigger an email that would go to the relevant parties. And if all those relevant parties approve the information that is part of the email, we will then go ahead and execute the transaction or move ahead with the supply chain process. Okay. And what we have created is actually a protocol. You see the flow chart on the right side. So the flow chart is describing how this is going to operate. So what we basically did is we have created a protocol, and this protocol will have the message that needs to be validated by the parties that are part of the supply chain, and then some expiry date. So this email will go to the concerned parties in a multi-stakeholder applications, and they have like fixed time. Let's say they get 6 hours to respond. Within those 6 hours, they can either approve the information that's part of that email or deny that information. And then this within those 6 hours, they will have to respond. And once the information gets back to the core server, it will process the response. It will check whether majority of the people approve the email or approve the message that was part of the email. If majority of them approve, then the business transaction will go ahead. Okay. So why this is important, and why do we need these kind of consensus, or why we need human-centered consensus? Because if you look at real world, we can't translate all our business operations into smart contract or computer logic, because there are some gray areas still. It's not black and white. You can't code everything in blockchain as true or false. Okay, so there are some things that requires experts to weigh in. So that's why we are connecting experts through the emails, and emails are something that they use on a daily basis. So they can actually provide the response through the email. So that's why we are building a human-centered consensus. Compliance management is one example where you have exporters and importers working with various jurisdictions, various countries, various customs agencies. Therefore, there are different rules, and there are slight variations between regulations in different countries. In such cases, we want human to weigh in. So therefore, we want to have a simpler mechanism for bringing in human to the consensus process. So that's why we build this human-centered consensus protocol. Similarly, some business transactions are risky. For example, in many multi-stakeholder applications, you may have to transfer data from one account to another account, and you want to be 100% sure that the services are correctly provided to you before you go ahead and transfer data. So again, in such cases, you can have human involvement, and they can check the information that's part of these process, and they can verify that everything went through correctly. Now we are ready to go ahead and proceed with the payment. So again, we can do it with blockchain rule-based consensus, but again, we may not be able to capture everything in that smart contract. So that's why we want human to weigh in here. So again, in these kind of applications, these human-centered email-based consensus is more useful. And I think that's one of the reasons why we are exploring this idea here in our research group. So in the next work, which is the last part of the presentation, is about verifiable computation for business processes. Again, this is an ongoing work here at QUT. So I'll explain what I mean by verifiable computation. So if you look at the diagram on the left side, let's say that you're having COVID symptoms and you're going to a testing lab and giving your swab for testing, and then you get a test result saying that you're negative for COVID. But can you be 100% sure that the lab actually analyzed your results before giving the swab test results as positive or negative? The reason why I picked this example is this has happened in many countries. And if you go to Google and type these keywords, you will read a lot of cases that happened like this, that people gave samples, but then they got incorrect test results, and they had to do Byzantine fault tolerance in real world, go to multiple labs, get many times tested and come to a conclusion whether they were positive or not. Okay, so again, we don't have any visibility into the lab's operation. Therefore, we can't be 100% sure whether the test was carried out correctly or not. Okay, what we are getting is only the result. Similarly, if you're familiar with cloud computing, if you have an application that you want to run on a cloud computing platform, and what you do typically is you buy a computing resource and you run that application on the cloud. So if you look at the diagram on the right side, let's say that you want to count the number of cars in an image. It's an object detection application, and you're offloading this object detection task to a remote cloud computing platform. And then the remote cloud computing platform is giving you the results saying that there are 3 cars. Okay. But again, can you be sure that the remote computer correctly executed the code? Do you have any evidence? Because that remote computer can simply guess there are 3 cars, 5 cars, 7 cars, 0 cars, 1 cars. It can randomly guess and still get away because you are not doing any secondary verification. Okay, so you are fully forced to trust the remote computer, and in some cases you are making some additional further decisions based on the data that you get from the remote computer. So again, the problem here is we don't have any credible proof coming from these remote nodes that the computation was carried out correctly. So what we are asking with verifiable computation is, can we ask these remote platforms to provide evidence justifying the correctness, okay, meaning that they actually carried out the computation and this is the right result, that was part of that computation process. This is where we are introducing Verifiable Python, which is an extended version of Python. So Python is a programming language that's very widely used today for machine learning and other types of applications. What we did is we extended this Python with verification capability. I'll explain what I mean by verification capability. So if you use our VPython or Verifiable Python, if you execute the code using VPython, this software is actually generating some proof in the background. And these proofs are nothing but runtime traces. Okay, so when your Python program is executed, there is something called interpreter. That's the one that's executing the code in Python. So what we are doing is we are gathering some proof or evidence in the background while the code is running in the foreground. And then once the code is completed, or once the execution of the code is completed, you are not sharing just the result, but in addition to the result, you are actually sharing these runtime traces as proof. Okay, so now when you are getting the result back, you have some additional evidence. Okay, this computer has actually executed the code and is providing some additional evidence. So on the right side, I have a scenario where you are a problem proposer, that you have a computation problem, and you're giving that problem to 2 solvers, that's solver A and solver B. And if they execute the code using Verifiable Python, they will produce not only the result, but also proof in the form of runtime trace. And this proof can be given to the verifier, and the verifier would compare these proofs. And if they match, you can be sure that the remote computer actually executed the problem correctly. Okay, so that's the Verifiable Python or verifiable computation that we are currently working on here at TUT. The part of the framework is already published to IEEE Blockchain Conference, but there are still some elements that needs to be improved, which we are working on at the moment here at TUT. I would encourage you to read this paper if you would like to understand how such a framework can be used in a real-world application. So here we are actually applying Verifiable Python to fake news detection, but it has many use cases which we are currently exploring here at TUT. That brings me to the end of my presentation. So as you can see, many of the real-world applications involve several stakeholders, but then we still rely on centralized solutions for connecting these stakeholders. While blockchain-based solutions are promising for these kind of scenarios, they are still suffering from this garbage in and garbage out problem, because they may still get information that cannot be trusted or that cannot be verified. This is where we introduce 3 different frameworks of solutions. Trinity is one solution for trusted data sharing, and a human-centered consensus allow human to involve in the decision-making process for multi-stakeholder applications. And a Verifiable Python is a promising platform for gathering proof when you're offloading computation to remote platforms. So just to summarize, these platforms that we have reviewed today, they are actually human-centered and verifiable, meaning that you have some means or methods to either involve human or verify the operations. And we can do both trusted data sharing or trusted computations with these. And hopefully these solutions help us minimize the impact of garbage in and garbage out problem in blockchain-based systems. And these are some resources for you to check out later.
Are there any questions?
saying the result and the proof are provided. So can the proof be verified independently rather than asking another computation? When we had the example of A and 2 and 3. But do we really need two people all of the time? Or can I verify the proof myself?
That's a big question. Yes, you can verify the proof yourself, but at the moment, the way we built the framework, we wanted to have strong guarantees. So again, we can tune the level of guarantees for these. And also we are coming up with some extensions in the near future, which would help us to get rid of the additional nodes. But now the way the framework is built, we need additional nodes to provide strong trust guarantees. Without them, you have some proof, but you are still not 100% sure. You know that they have done some work, but you can't be 100% sure. That's why in the current protocol, we have multiple nodes. Now, if there is a sort of similarity, then we can be 100% sure. Going forward, we are building techniques that can get rid of those additional nodes. We're in fact exploring this for even smart contracts going forward, because this is what smart contract does. You need someone to do computation, but at the same time, you want to be sure that they did the computation correctly. So I think there is a potential to explore in that context.
There are a lot of questions I would imagine, in the sense that how much overhead is it to conclude these cases?
Yes.
How bulky is this proof? And on the verifier, and how much time?
Again, so far, the first version that we built was really heavy and was taking more time. Now we have already optimized. We've already identified more places for optimization. So I think it's a promising direction for our research group going forward. Yeah.
Thank you. Rasha, I think we should start a bright for 5 minutes. Let's do the bright.
Yeah.
Thank you.
And then we'll try to incorporate you